Hello, this is Kyung Hee University's Department of Architectural Engineering and High-Rise and Special Structural Design 2019 project. Midas analysis of the load test according to the angle change of the DIAGRID. I'll explain the design plan, the Midas analysis, and the conclusions. The planning part has motifs, structures, and plans. We tried the same design as the Sears Tower, a combination of a setback structure and a bundle tube structure. Bundle tubes, unlike normal tube structures, are connected to each other by two or more tubes, reducing the shear lag phenomenon, a disadvantage of the tube structure. This has the strength to achieve greater lateral stiffness. And Sears Tower is an externally setback structure to prevent wind loads that increase as the height of the building rises, and a belt truss is installed on the outer wall whenever the floor area changes. We wanted to know how much structural stability it would be if we actually put together a DIAGRID structural system in a bundle tube structure. If the existing Sears Tower and the setback structure have secured structural rigidity, we have applied a diamond to reduce the volume further. We chose LA as the site because we want to design buildings in strong earthquake area. The displacement limit was set to 1/400 th, and the base floor was set to 4 m, and the building was designed with 100th floor. We compared the reduction of lateral displacement by comparing the base building with buildings with DIAGRIDs at different angles and locations. Next is Midas analysis. This is the steel type and dimensions of each floor steel member that we first set. We selected members with high frequency of use within the KS specifications. The wind load condition is based on KBC 2009 and the basic design wind speed of 30 m/sec corresponding to Seoul is applied. The importance coefficient is set as follows. The maximum design wind speed calculated is 50.386 m/s. The floor loading conditions are as follows. Seismic load conditions are as follows. The model refers to the IBC code as a steel skeletons with an effective ground acceleration of more than 0.4 g. This is response spectrum. Short period design spectral acceleration of maximum value was added when inputting response spectrum to ensure that seismic loads were reflected. Quantity value of base model without DIAGRID. Based on this quantity value, the quantity value of the models by the angle of the diamond grid has been unified. Because the wind load displacement h/250 is greater than the target h/400, we wanted to solve this problem by applying a diamond grid. The displacement of 37 degrees was 0.66 m, with a period of 5.2 seconds. The 62 degrees displacement was 0.70 m, with a cycle of 5.48 seconds. The 82 degrees displacement was 2.29 meters, with a period of 10.14 seconds. The 82 degrees model has significantly lower structural performance than the base model. A 37-degree diamond grid was effective in reducing lateral displacement and period. The result of the reference paper was that there was an optimal angle between 65 and 75 degrees. The difference between the paper and the model was the presence of corner columns, bundle tubes, and setback structures. These are the components that are used very often within the KS specification as mentioned earlier. The initial use member has been modified through Midas interpretation to the following. The final model was designed in the following steps. The displacement of the final model was very strong with AH/5479 and a period of 3.7 seconds. Therefore, it was considered inefficient to apply the building-wide diamond grid. Therefore, partial application of the diamond grid was considered. Structural system sensitivity analysis results by DIAGRID location. Models without DIAGRID had displacement H/104. Period 12.27 seconds. The case where the grid is applied to floors 1 to 8 has a displacement of 3.82 meters and a period of 12.27 seconds. The case on the 53-60 th floor of the grid has a displacement of 3.77 meters and a period of 12.82 seconds. The case with the grid on the 61-68th floor has a displacement of 3.77 meters in a period of 12.95 seconds. The case where the grid is applied on the 93-100th floor has a displacement of 4.06 meters in a period of 13.26 seconds. Case 2 with the least displacement was the most effective for the same volume. Displacement and period values when grids are applied to parts other than the case. DIAGRID were applied to areas where the setback structure caused elevation changes. Midas structural analysis has determined the dimensions of the member. First, the dimensions of the box member. Dimensions for H-section members. Dimensions for pipe members. This is the final design model. The bottom shear force by dynamic analysis. 110,320 knots in the x direction and 108,190 knots in the y direction. The bottom shear force by static analysis. 85,028 knots in the x direction and 85,028 knots in the y direction. The analysis did not require a scale-up factor. Before analyzing the mode shape, we found that the mass participation rate was 95% or higher. The behavior and frequency of the analyzed mode shape. Primary mode. Secondary mode. Third mode. This is the result of the review of interlayer displacement due to earthquake load. We calculated the displacement coefficient interlayer displacement of the adopted structural system and confirmed that the result value was within the allowable range. Results of maximum displacement due to wind load. X-directional maximum displacement 0.65 m, Y-directional maximum displacement of 0.95 m, was found to be less than H/400 m. Damping sensitivity analysis. For damping 1%, 4%, and 7%, the bottom shear force in wind load displacement and dynamic analysis was checked. Displacement when damping 1%. Period when damping 1%. Underground shear force by dynamic analysis in the case of damping 1%. Wind load displacement at 4% of damping. Period at 4% damping. Underground shear force by dynamic analysis in the case of damping 4%. Wind load displacement at 7% damping. Period when damping 7%. Underground shear force by dynamic analysis in the case of damping 7%. A comparison of the bottom shear forces by dynamic analysis according to the damping. The wind load displacement was found to be smaller as the damping grew, and the bottom shear force by the seismic load dynamic analysis increased. Because the scale-up factor according to damping is all less than 1, the scale-up factor is left at 1. Finally, the conclusion. Shear lag of tube structure. You can see that the beam tube structure and DIAGRID complements are made up. Quantity calculation. The ratio of steel aggregate to height width per floor area was compared to the volume of existing buildings in the table. 37.52 degrees was most effective when compared with the reduction of lateral displacement and volume according to the angle of the diamond. The lower part of the setback structure was most effective when comparing the lateral displacement reduction with the position of the DIAGRID. Midas analysis during the load test with varying angles of the diamond. Thank you.